Hi, this is Mike Tonchik, President of Dairyland Electrical Industries, and today's topic will be insulated joints in combustible atmospheres. So let's look at this topic together. What exactly is an insulated joint? Well, it has these functions. It would be insulation to prevent metallic contact between pipe sections. We don't want one section of pipe that has cathodic protection to be bonded metallically to a grounded section or to a different cathodic protection system. So insulation systems are used. As a consequence of having an insulation system, though, it does mean that voltage could be established across the insulated joint, and then the joint will have to withstand that voltage. So what exactly is an insulated joint type? Well, there are three different types, mainly in the industry. There are monolithic joints that are weld-in joints. These are factory pre-made insulation systems that would be welded in by an operator, and that pipe segment has an internal insulation system within it. Then there are flanged isolation joints, and these would be bolted flanged sections of pipe that have an insulation system between the flange faces, and there'd be sleeves and insulated washers to keep the bolts from bonding across. And then finally, the smallest of these types of objects would be an insulated fitting or a union. So in a measurement line, you might have this small isolated fitting to keep one section of tubing separated from another. Here's an example of what some of these objects look like. So in the upper left, we have a monolithic joint, and with the cutaway, you can see a yellowish section, and that would represent the insulation system that separates the right half of the pipe from the left half. Or on the upper right picture, you can see a bolted flange where two flange faces come together with the insulating gasket, and then you can also see the bolt or stud with its sleeve, and then insulated and steel washers. So the insulation systems are those that are touching the flange side. And then finally on the bottom, here's an insulated fitting, sometimes called a swedge-lock fitting, where insulation material in that union keeps the left half metal tubing section and fittings from the right half. So what can these insulated joints withstand? If they're going to be subject to voltage, how much voltage would they be exposed to, and how much can they handle? Well, they might be exposed to any level of voltage, but what they can handle is really the main issue here. A small insulated fitting or union might handle hundreds to low thousands of volts at best before there'd be some kind of insulation breakdown or arc. A flange joint is a field assembled joint. So again, it's subject to how the operator put that joint together. Realistically, it could handle thousands of volts, again with variation depending on installation. Probably the most consistent would be a monolithic joint, because that's a factory made assembled kit. And there, those can handle up to, say, 25,000 volts. You're talking tens of thousands of volts for that one. So what kind of risks could occur related to insulated joints in hazardous environments? Well, first, there could be voltage risks for personnel. This might not establish an arc, it might not cause damage, and isn't specifically related to combustible atmospheres, but clearly any insulation system that can withstand voltage or support voltage could present that voltage to personnel that are working nearby and touching the structure. But if the voltage were to reach some very substantial levels, there could be enough voltage to result in an arc across the insulation system. And then further, that arc would damage insulation, it could possibly damage the steel, and finally it could ignite either a combustible atmosphere outside the joint or possibly the product, pipeline product contents inside the pipe. So what do regulations say about this topic? Well, there actually are some. In the gas industry, CFR 192 in the U.S. regulates those interstate pipelines that fall under this section, and it has a particular reference that talks about this, and I'll read that section. It says, an insulating device may not be installed where a combustible atmosphere is anticipated unless precautions are taken to prevent arcing. And I've underlined some of the words that are of interest, probably because some of those words are not very well defined. We need a little bit more detail to know what is that really saying. So let's look at that further. An insulating device would be those very insulated joints we've been talking about, so some kind of fitting or a flange or monolithic joint. It brings in now a combustible atmosphere. So what is that? Well, that's going to be a hazardous location, a defined classified location where explosive gases are present, but they don't say what that is here. They just say that there's this risk. Then they say that you must take precautions, which clearly means you have to do something, but they don't tell you what to do. And the ultimate goal is to prevent arcing, and that's the risk that we're trying to address. Well, there's another regulation section immediately following that one, which says this: where a pipeline is located in close proximity to electric transmission tower footings, it must be provided with protection against damage due to fault current or lightning, and protective measures must be taken at insulated devices. So once again, we have more things to talk about. What do these things mean? And I've underlined the topics of interest. So where something is in close proximity, obviously it's implying it's nearby, but they don't say how close. They do name transmission towers, so clearly this is the source of your troubles. This is where the risk would come from. And it will actually be that's where the source of the AC fault current would come from, or even lightning if it was to strike that structure. Protection is needed, which again says you must do something, but they don't say what you must do. They do name fault current and lightning as the risks. So we know what the hazard is, but it doesn't say what the degree is of the risk or how it got on the pipeline in the first place. You must take preventive measures, again, but not defined. And they do talk about insulating devices, pointing out that they're at risk if there's fault current or lightning conditions. So overall, between these two sections that we've looked at, the language is very general, which would be typical of regulations. They're trying to be broad and catch concepts and the principles involved without getting lost in the details. However, the problem for the user is there isn't enough detail to know exactly what to do. So these are the things that we'll have to dig into. So we really need to look at three main things in order to parse this section and do something useful with it. We need to know something about what constitutes a hazardous location and how sites are classified. We need to know something about AC and lightning risks, and also I'm going to throw in one more, and that's static charge, as that could be an overvoltage condition. And then how do you put these together to provide protective measures that are effective for insulated joints? Well, hazardous locations are classified in various ways. In the U.S., the National Electrical Code, NFPA 70, Section 500 actually defines what are hazardous locations, and it further goes on to explain what kinds of practices are allowed and products are allowed in those areas. Other countries and other types of systems have the same kinds of definitions. So CSA in Canada and other systems like ATEX definitions for Europe and further. For the energy industry, we're only going to look at combustible gases as the main concern. If our industry was something to do with grain elevators, then we might be concerned about combustible dusts that could ignite. But here we're strictly going to look at gases. We also need to divide the locations into high risk or low risk or no risk to know what kinds of products or methods are allowable. So there are those definitions out there. So let's look at the three main classifications for hazardous locations. Just to start out, this isn't a hazardous location, but it's the opposite of one. An ordinary location is where there's no combustible gases at any time that are present, so there's no risk. And that would be most offices and warehouses, manufacturing sites, even pipeline locations if they aren't classified. The next level up is a Division 2 or Zone 2 location where there are gases present, but only if something fails, or only for a small amount of time of the total exposure in a year. So those are deemed to have a low risk. And then there's Division 1 or Zone 1 locations, which generally have a high risk, and gases are presumed to either always be present or be present for a significant portion of the time, enough to classify it that way. In North America, we would tend to refer to divisions as being our definition for hazardous locations. But other parts of the world will typically refer to zones. And so that's how this breaks down. It's just differences between standards. And not all standards are standardized. Hazardous locations are also further broken down into different gas groups. And this mainly addresses the flammability of the various gases that could be present. And there are different gas groups that follow divisions and zones. In the division system, we would say that there are gas groups A, B, C, and D. And in the zones, we would say that there are gas groups 2C, 2B, and 2A. But you'll notice on the table that they follow each other and they can be related. This can get a little confusing because one system uses letters that are inverted compared to the other. But what it's really showing is that some gases are more easily ignited than others. So acetylene would be much more easily ignited than propane or methane. So it would have the highest ignition risk for a Division A or a Zone 2C gas group, and the lowest ignition risks would be in gas groups D, or for zones it would be 2A. So graphically showing this, there are the Division 1, Division 2, or ordinary locations, or Zone 1 and Zone 2 and ordinary locations, shown for typical installations in some guidance documents. So here's an image that came from an AGA document, and it's graphically showing the Div 1 and Div 2 in ordinary locations. Here's a gas vent or relief valve, and around that release point, you can see for a radius of 5 feet that that's considered a Div 1 area, so high concentration of gases expected. That's surrounded by a Div 2 hazardous location out to a radius of 15 feet from the release point for the gas. And then outside of that, you see an ordinary location. So most of this site looks like it's Div 2, including the inside of the building, the area 15 feet away from what looks like a valve site. And you notice even low points like trenches, those are assumed to have gases present in them, settled in the areas, and that's considered Div 2. And then outside of that is ordinary. The typical Division 1 site is shown in this kind of a picture, where we have a tank sitting inside of a berm, so it's in a low point, and here we're dealing with jet fuel. So the insulated joints that are present here are sitting in an area that's considered Division 1 because it's assumed that the gases would be trapped and settle in this low point. So typical construction around tank farms with berms, it's commonly Div 1. In comparison, if that same insulated joint were outside of a building, above grade, available to the free air movement, this is typically a Div 2 site, and you might be able to use a different product here. So these are the classification examples. There are reference documents that would help someone classify their site if an engineer at your facility did not already classify the site. That's actually the most common, is that someone will have told you what the classification of your site really is. But if there was no guidance, you could turn to documents such as those put out by AGA, American Gas Association, or API, American Petroleum Institute, to get that type of guidance with the images like the type I just showed. There would be some guidance from CFR 192 and 195 and from the National Electric Code. And of course, there's other documents as well. An interesting point about CFR 192, which again is for the gas transmission companies, is that there is a note at the end of that document that the National Electrical Code for the U.S. is included by reference. And what that does is it gives specific detail now to the CFR wording because of including the National Electric Code by reference. So what constitutes a hazardous area or combustible atmosphere? Well, those that are stated in the National Electric Code. And what kind of products can you use appropriate for that site? Well, those that the National Electric Code says you can use, and also installation methods. So this is where you get a bit of detail. Interestingly and strangely, CFR 195 doesn't include that reference to the National Electric Code, but you'd still use that for best practices or guidance. So again, over to products that are acceptable for use. If it's Division 1 use, you will typically see a cast aluminum box with a whole bunch of bolts holding down the cover, and this box is meant to contain the explosion. It's actually assumed that gases have worked their way into the product, and there could be an explosion within the product, but it can't translate outside into the surrounding environment through the threads or the fittings. So this is considered flame-proof construction or a flame-proof protection method. So that's suitable for Div 1, the highest risk areas. In Division 2 sites, you will not typically see cast aluminum boxes. You'll see other methods of construction that could vary. Could be something inside of a fiberglass box or a molded housing. It could be plastic. But these are all two different protection methods, the most common of which would be the non-sparking protection method or construction. The concept here is that it doesn't produce any heat or create sparks enough to ignite a gaseous mixture. Now, something that can get awfully confusing for folks is that both of these products or methods are all considered explosion-proof. It's just that it's to different protection methods and different construction. So the term explosion-proof often gets confused, and people think of the cast aluminum boxes as only being those that are suitable for quote-unquote explosion-proof areas, when really you just have to use the right product construction for the right hazardous location, division, or zone. And then further, certification is needed for product use in any hazardous location, both for the division or zone that's appropriate and also for the gas groups, amid some other requirements. So here would be typical product construction. On the left for Zone 1 or Div 1, you'd see, again, a cast aluminum box. And on the right, you'd see, in this case, a fiberglass box. Could be various types of construction for a Div 2 site. Now let's look at some of the electrical hazards that actually produce the voltage that produce the arcing at different sites. Typical scenario like this, a gas line feeding a power plant means that power lines and pipelines are going to be in close proximity. So the hazards that could produce overvoltage and affect an insulated joint would be lightning, which could show up at almost any location, although it can vary around the world as to your incidence of lightning, but we would generally assume it could appear anywhere. Some sites have AC induction present, and the AC induction would come from overhead power lines. Some sites further then are subject to AC faults. And just a side comment, if your site has AC induction on a pipeline, then it automatically has an AC fault risk. And the telltale is the AC induction that you could measure with your meter. Some sites also are subject to static charge buildup. So an example would be the jet fuel line in that earlier picture. The movement of that fuel could have suspended charge that actually shows up on the pipe. Let's talk about lightning. Here's an interesting map that shows the incidence of lightning around the world, and you can see that some areas are subject to much higher incidence of lightning than others. Being from the Midwest, it's hard to imagine that everyone isn't subject to lightning like we are, but if you look along the west coast of the U.S., you can see that they have very low incidence of lightning, and other parts of the world have either high or low as well. So useful to know how your area would generally fall. lightning waveforms can be standardized. These are very fast rising waveforms, and it's unlike AC power. A lightning waveform or any kind of transient is going to have a much faster rise time than an AC waveform. And that fast rise time causes some problems with producing high voltages, which can then easily cause arcs. In this picture here, this is the waveform shape of what's called an 8 by 20 microsecond waveform, where the rise time on the left is 8 microseconds, and then the decay down to half of the peak value occurs in 20 microseconds. There's various industry standard waveforms, but this would be the most typical high current waveform. Here's an example of what lightning can actually do out in the field. Here's an example of an insulated flange, a bolted flange, where an arc has occurred from the steel washer over the insulated washer to the flange face, and you can see the marks all across in between where an arc has occurred. You can see loss of paint and some damage. Here would be another image of lightning damage, and here there's distributed small arcs, again from the outer steel washer over the insulated washer to the flange face, and you can see small amounts of damage. The problem with arcing is that it leaves carbonized material, and it generally can continue to act as an electrical path, a breakdown for further current flow. So generally, these types of problems need to be found and repaired to establish the insulation system again. Now over to AC hazards. There are AC induction examples where you could measure induced voltage on your pipe. These are more hazards for personnel and possibly AC corrosion issues. These don't tend to result in arcing themselves under steady state conditions, but they certainly are real hazards. However, the indicator of induction, steady state induction, shows that there is a coupling effect between the power line and the pipeline, and you could easily have an arc when you have an AC fault in the power line. And that is enough of an event to damage an insulator or cause steel damage. And the arc could either ignite pipeline products, or it could ignite a combustible atmosphere surrounding the pipeline. Either way, it could be quite an event. So in the standards, or the codes, CFR 192, again, is just raising the awareness that pipelines that are near power lines have this kind of risk to the pipe steel and insulation, but also to insulated joints that are in the pipeline. If you have liquids pipelines that can build up a static charge, that will happen as the liquid flows, and you could have a voltage across insulators, again, which could arc. This is a really low energy event, surprisingly low amount of current flows in static charge, but it is a high voltage, and that difference still could cause an arc and ignite product. Let me talk about the consequences of lack of protection. I'll give you some examples of events that have occurred that would represent these kinds of hazards: insulated joints, insulated systems in combustible atmospheres. At a gas distribution facility in New York, there was an AC fault on a nearby power line, and that fault affected the pipeline, and an arc occurred at a gas sensing line and arced across a small fitting. It easily burned through the tubing, and that resulted in a leak and an ignition of the product, and it burned the entire station down. In Ohio, there was an oxygen line at a steel plant, and an AC fault there produced an arc, and that resulted in an explosion and substantial damage. Likewise, in Indiana, there was an AC arc at a road casing and resulted in a fire. An example of lightning would be at a Florida gas facility where lightning hit a facility, arced across an insulation system, and the entire facility burned. So there can be very substantial results from lack of protection. Now, how would we actually provide solutions to prevent arcing? The first step is to know how your location is classified. Div 1, Div 2, Zone 1 or Zone 2. Following that would be using best practices on protection methods to address those hazards and to use suitable products that are appropriate for each classified area. So what kind of best practices exist? Well, for fast rising waveforms like lightning or static, protection products should be installed with a short conductor length attaching those to the insulated flange or fitting. The reason is there's inductive effects that show up, and fast rising waveforms can produce a very high voltage when the current attempts to flow through this inductive path, meaning a wire. So if conductors are kept short, and short here meaning ideally less than 12 inches in total, then the overvoltage resulting across the insulation system can be kept manageable and prevent arcing. An even better method for reducing this cable effect relating to inductance would be to use bus bars instead of wires to have the lowest resulting overvoltage. Here's an example of good practice using short conductor length. Here a monolithic joint has had welded tabs put on the pipe and on the joint so that a protective product could be mounted with a very short cable length. So again, a very good installation here. In this installation, this is a bolted flange, and here the distance you can see on the pipe that a protection product has been mounted on a post very close to the insulator such that short cables can connect to each side of the flange, resulting in very good protection. And finally, here's an example of a protection product which has probably the best approach, and that is using some kind of bus bar mounting system where appropriate to have a low inductance path across the joint and the lowest resulting voltage. Here, the product is supported by these brackets, and it's the conduction path as well. Don't forget that there's multiple isolation devices commonly installed, and all of those need to be protected. So here a protective product is shown connecting across a series of about 5 insulated fittings, and they're all connected with one device. There might be some conductor length issues in this example. However, you're far better off protecting this joint to deal with all of the hazards and suffer some additional cable length issues than to have no protection across these kinds of joints and then result in arcing and possible fire. So finally, you have to use suitable products that are appropriate for the right type of location. So a Div 1 device would be used in a Div 1 area, and likewise in a Div 2 area you'd use a Div 2 rated device. Any appropriate product could be used in an ordinary location because again it's not a hazardous location then. Any device used really needs to be rated for both lightning and AC fault current. I would say that should be the default. There could be some locations that have no exposure to fault current or perhaps no exposure to lightning, but I would claim that most locations actually have exposure to both to reasonable levels. Lightning ratings typically are to 75 to 100 kA as a peak value of current, and typical AC fault ratings for protection products are in the several thousand amp range, so I say perhaps 3 to 5 kA. So in the end, we want you to stay safe. Hopefully these practices will keep you safe. There are more topics and more subjects related to this matter, but this is meant to be an introduction to the key points of hazardous locations, appropriate products, and appropriate installation methods. But if you have additional questions, feel free to contact me. Thanks for listening.